Hello, my name is Charles Taylor from the University of Leeds. I work in the School of Mathematics, and today I'm going to talk about the central limit theorem. It's a very important theorem. It sounds very grand, and in some ways it is grand. And what we're going to do today is really just talk about why it's important and just state the result and different applications of its use. So first of all, we're going to look very quickly at the normal distribution, just to revise our knowledge of that. And then we're going to look at the distribution of the sample mean and how we might explore that concept, and then see how the normal distribution can be used to approximate that distribution and the applications, the main really thrust of the uses of the central limit theorem. So the outline is a little bit of revision, the statement of the theorem, an application of the theorem, an approximation, and then some further uses. So the normal distribution, first topic, is used for many data sets. Many continuous type data sets have a curve which is a nice bell-shaped curve which we can successfully model with a normal distribution. We also have the case that many discrete data sets can be modeled by a normal distribution, and this occurs where you have a very fine resolution of data. So for example, exam marks, which are usually recorded to an integer from 0 to 100, if you have lots and lots of students, you very often get a nice bell-shaped curve from these values. Of course, it's not exactly normal because you don't get values like √2 occurring in exam marks. So it's not precise, but it's good enough for most purposes. And of course, there are many distributions which are not normal at all. And we mustn't forget that. So a bit of notation. So if we have a random variable x, which has a mean mu, Greek letter mu, and a variance sigma squared, we write that as n mu sigma squared to denote the mean and the variance of the normal distribution. For a normal distribution, we can standardize the random variable by subtracting the mean and dividing by the standard deviation. And so if x is normal, then z, which is a transformed x, with subtract the mean, divide by the standard deviation, is also going to be normal, and the mean of that transformed random variable is 0, and the standard deviation, or the variance, is equal to 1. And so if x is a general normal distribution, then x minus mu over sigma is a standard normal distribution.